Hi guys. So in this next chapter, in this next unit, we're going to look at atoms a little bit more closely. Um, Back when you guys were drawing particle diagrams in the matter unit, we represented atoms as circles. But what we know the atom looks like today is a lot more complicated. We know that atoms are actually made up of tinier particles, um, and we drew them as circles for simplicity's sake. So what we're going to look at first is the history of atomic structure. So years and years and years ago, when there was very little research being done on what the makeup of matter was, and technology was not that great, scientists had an idea of what an atom looked like, but that idea drastically changed over time as more research was done and technology got better. So, first, we're going to talk about Democritus. So, he was the first scientist that thought matter was made up of tiny particles. So, let's write that down for him. Matter is made of tiny particles. Now, he imagined that the tiny particles that made up that made up matter looked like the matter. So, like here, I have an example of water. So he pictured water atoms to be like clear and blue and smooth, and he pictured them having like the motion that would look like water moving from the outside. Where the iron atoms, he pictured the atoms themselves being gray and being hard, and being kind of rough, because that's the kind of features iron has from the outside that we can see. So back then, everybody kind of thought he was crazy because he had no proof to back up his theory that matter was made up of smaller particles, until Dalton came along, and he was the first one to have an experimental working model of the atom. So he kind of had proof that atoms existed. So let's write that down for Dalton. Experimental working model of atom. Okay. So looking at this diagram here, we can kind of come up with the five parts of Dalton's theory for atoms. And the first part that's important is what he thought the atoms looked like. He thought they were indivisible, meaning they can't be broken down. Indivisible solid spheres, just like you see in the picture. Okay. Second thing that he thought, that atoms of the same element must be identical. So if you look at this example here, if you look at hydrogen, so here are my two hydrogen atoms. Because they're both hydrogen atoms, they are identical in mass. He actually did his research by studying mass. So he thought if they were if they were atoms from the same element, they must be the same exact size. Neither one of these first two parts of this theory are actually true today, but we will get into that later on. Okay, the third part of his theory, he figured out that atoms can combine to form compounds. Okay, and there's two important things that are going to go along with that compound idea. So the first one was the law of definite proportions. And you guys kind of already know this idea. We just didn't really give it a name, because in the matter unit, when we studied compounds, we said that the definition of a compound is when two or more elements chemically combine in a fixed proportion. Okay, so for example, to make a water molecule, you have to put together 2 hydrogens and 1 oxygen. It will always be 2 hydrogens and 1 oxygen, and one water molecule will always have a mass of 18 AMUs. If you change the ratio of elements in a compound, the compound's identity will change. You will be changing it into a different compound. So an example, we can just use water as H2O. Always 2 grams of hydrogen and 16 grams of oxygen. Okay? Now, to talk about what we said before about changing the ratio, he also stated the law of multiple proportions. So that was basically saying that the number of atoms in a compound can change, but that's going to have the compound having a different identity. So for example, H2O is water and H2O2 is hydrogen peroxide. Both compounds are made up of hydrogen and oxygen, but I went ahead and changed the amount. They can bond in different amounts, but when they do that, they're a different compound. Okay, so he said all of those things. And guys, within all of these theories that he came up with, he also was kind of the first one to prove conservation of mass. Okay, by studying chemical reactions and measuring the mass of the reactants versus the mass of the compound we formed at the end and noticing that they're the same, he was able to also put a name to that. So he was kind of the first one to get credit for the discovery of atoms because he had evidence of them, unlike Democritus. Okay, so now some years went by, and J.J. Thomson, he did an experiment with cathode ray tubes. So basically, this is what it looks like, and I'm going to show you guys a demonstration the next time I see you in class because we can look at this in real life. So inside of this cathode ray tube, this is just a glass tube, so you can see through it. This is glass. So right here is a piece of metal. And what happens when you add an electric current to this metal is you get a flow of, or a beam of radiation, okay? And the beam of radiation is coming out of the metal. So 2 things happen that J.J. Thomson thought were important. The first thing that he noticed was as this beam of radiation was leaving the metal didn't disappear. So you would think, well, okay, if particles are leaving matter, then over time the matter is going to disintegrate. The matter is going to get smaller. Because the metal never got smaller, he was able to assume that the particles that were in that beam of radiation were actually smaller than atoms. If atoms were leaving the metal would get smaller. But that didn't happen. So the metal didn't disappear. So the particles that are in that radiation are smaller than atoms. And he actually figured out that the particles that were leaving the metal and in the radiation were this much smaller than the hydrogen atom, which is the smallest atom. So that's so tiny that it's almost irrelevant. It's almost non-existent. The second thing that he noticed, so when we took magnets and we placed them near this beam of radiation, notice that the beam of radiation, it went towards the positive side of the magnet, and it bent away from the negative side of the magnet. So if it's being attracted to the positive side and it's repelling away from the negative side, what does that tell you about the charge of the beam or the particles in the beam? They must be negative because opposites attract and like charges repel. Okay, so if we look at this next picture of what J.J. Thomson thought the atom looked like, we call this the plum pudding model. So plum pudding is like an old English dessert. It's almost like bread with like raisins scattered about inside of it. If you guys can't picture what that looks like, this is almost as if you have like a ball of cookie dough. So he still agreed with Dalton that there's this solid sphere that he still agreed with, but he said, well, the solid sphere also has electrons in it. And he pictured those electrons as being embedded in the solid sphere, just like chocolate chips in cookie dough. He still believed that the atom was overall neutral, like Dalton did. So this solid sphere must be positive to cancel out the negative electrons. All right. So that's what cathode thought. That's what Thomson thought, and he figured all of this out using his cathode ray experiment. Okay. Now, Rutherford, especially for the Regents, guys, Rutherford made a really important contribution to what we think the atom looks like. So his gold foil experiment is very famous. And what this is, see here we have a radioactive source. So radioactive elements, they emit radiation. And one type of radiation is alpha particles. And alpha particles are positive particles. So what he did was he took a piece of gold foil. So literally, guys, like aluminum foil is made up of aluminum atoms. Gold foil is just a piece of foil made up of gold atoms. So he took this radioactive source and he shot alpha particles, he shot positive particles at this gold foil, and he watched what they did. And he noticed two really important things. He made two really important observations. Some of the alpha particles, this is important, and I want you guys to write what I'm writing. Some alpha particles were deflected, meaning they hit the gold foil and they almost like bounced backwards off of it. He also noticed most of the alpha particles, and I want you guys to underline the word most because that's important, most of them passed right through. So he's like, okay, well, if atoms are solid spheres, then I wouldn't have seen this happening. I wouldn't have seen most of the alpha particles go right through the foil if these big, dense, solid spheres were making up the matter. So he said, no, that's not what an atom looks like. He said, an atom looks like this. So the alpha particles that hit something and were deflected, since alpha particles are positive, there also must be something in the atom that is positive. But it must be really small, because if only some of the alpha particles hit it, it must not be an easy thing to hit. So he knew it was small, he knew it was positive, and he knew it was dense because the particles weren't able to go through them. So Rutherford basically discovered the nucleus of the atom. He knew that it was small, he knew that it was dense, he knew that it was positive, and he called it a nucleus. So basically, he discovered protons, which is the second subatomic particle. J.J. Thomson discovered electrons. He also said, okay, the electrons are there, but they're not embedded in the nucleus. They're kind of floating around outside the nucleus, but in between, the nucleus and electrons, why would most of the particles be able to go right through the atom? Well, the atom must have a lot of empty space in it. Mostly empty space. And that's a huge contribution, guys. That's way different from anything that Dalton or Thomson thought when they did their experiments. So I have a little simulation for you to look at. Okay, so in this simulation, these little tiny dots are the nucleus of the gold atoms, and the dotted circles around them, those are showing like our electrons where they're orbiting. And I'm going to turn on my alpha particles. And I just want you guys to watch this for a couple seconds. So notice what my alpha particles do when they get near the nucleus. They reflect. They deflect, I should say. They bounce away because positive and positive repel. And only some of them are hitting the nucleus because those nuclei are very small. So the chances of hitting into it are not big. Most of those purple dots, most of those alpha particles, if you look at what they're doing, they're going straight. They're starting at the bottom and going straight through to the top. And that's because mostly what we have in this picture is empty space. Okay, so that was kind of a big deal. All right, so guys, we're gonna get into later scientists in our next video. For right now, I just want you guys to make sure you understand this, and I'm gonna give you some questions to answer, and I'll see you in class tomorrow. Thanks, guys.